this recording. And you have a test week. I have a test week. Our test isn't until Monday. So I had to parking lot you guys for just a little bit while I get my other test done. And then this week, well, starting today, it's your turn. So I'll make you a practice test and post that with some solutions, and you'll be all set for Monday. I brought in the tables, but I'll also add a page here. Oops. Okay. Test number 1 on Monday. But like I said, I'll give you a practice test. It'll just be on everything up until that point, specifically chapters 1 through 3, and then we're in chapter 4 right now, and we're just gonna do chapter 4 light on the test. Okay, so 1 through 3, and then I'll call it chapter 4 light. Mostly because I don't think that we'll be able to wrap up all of chapter 4, but what I want to get through is 4.1, which is normal distributions. And 4.3, which is binomial distributions. The others we can kind of just sweep under the rug until after the test, talk about them briefly, and then move on. Okay? So that's what I'm hoping to do. Obviously, whatever we don't get through on Wednesday is not on the test, so I won't really know until Wednesday. All right, let's do, any questions about the test first? Nope. Haven't even thought about it, Emily. I know. Me neither. Last day we started the normal distribution. Now the normal distribution, we introduced some concepts, right? We have a normal distribution. It's centered on the mean, and on each side, we can fit approximately 3 standard deviations before the area under the curve gets super, super small, right? And so we said, okay, here I can fit roughly 3 standard deviations on either side. 3 SD, I guess. It's fine. The most important part that we introduced last day was that the area under the curve is a probability, right? And so here, the area under the curve is a probability. Some other things to keep in mind, right, are that these axes keep going to infinity and negative infinity in either direction, and they never close. So the curve never closes on the axis. There's always area under the curve. It's just super, super small, which means what? Means anything can happen, but the probability of it happening is very, very small. Right? And so what did we say? Okay, well, to be able to find this area under the curve, we would either use calculus, no thank you, right? we'd have to do an integral over the area that we wanted or the range that we wanted, and that sounds like a terrible amount of work. And so to find probabilities, we use the standard normal distribution. We use the standard normal distribution. It's got a bunch of different names like the unit normal, so they all mean the same thing, the standard normal distribution. Z. So then what we said was, okay, Z, we built up the formula for Z. Z is if I take some observation and I subtract the mean, so I have some observation X and I subtract the mean and divide by the standard deviation, what am I finding? I'm finding how many standard deviations X is from mu, right? And so that's the definition of Z. Okay, so Z is how many standard deviations an observation X is from the mean. Mu. Okay, so then what happens? Then if I reduce my original normal distribution, which was allowed to have any mean, any standard deviation, then if I've standardized, right, by calculating Z, then I get this standard normal distribution, which is centered on 0, right? And the standard deviation is 1, right? And these are all Z's on this axis, which means that it's going to taper off at -3 and +3. It's going to keep going, right? It keeps going to infinity and -infinity, right? So technically, I could find a very, very large value of Z, right? But the area under the curve is still the probability of something happening, right? And so if the area under the curve is super small, then the probability of that happening is very small. Okay? And we talked about, okay, well, what happens if I move into the tails past -3, right? Usually we just say, oh, the probability of that is approximately 0, right? And it's very important that you don't say 0 because it's not 0, right? Because these tails never close on the axis. We also introduced some notation. It's a busy day on Wednesday, right? We said Z is a normal distribution centered on 0 with a standard deviation of 1. Right? So that shorthand is going to be really useful to recognize. At least you don't have to use it, but you do have to be able to read it and understand what it means, right? Notice shape, center, spread describes the entire distribution, right? And so those are 3 things that we need, and that's still true. Okay. Whoo! We haven't even talked about the probabilities. Then we introduce the tables. And if you don't have a copy of the tables, I do have a couple more that you can grab later. But we did introduce these tables. Just snag a copy here. Add a page. It's a long review today, but we need it. It's been a long time. All right. What I want you to do is just really dissect that table that you have, okay? Because there's a lot of clues on there, okay? For example, it gives you a normal distribution. That's a good place to start. And it says that, okay, a Z value, if I give it a Z value by doing what? By feeding it, whoa, it's all jumpy here. By feeding it the whole number and the first decimal place, and then I can join it up with the second decimal place, right? Then that's going to be the Z value down here. Then we get a table entry, right, at the intersection. So for example, I'll use a Z of negative 3.36. I don't know why it was so hard to land on something. So now, if I wanted to find the area to the left of Z, which is centered on 0, Z equal to negative 3.36, let's say, right? I want to find what's the probability of finding something more extreme than this, right? So then we want to find this area, something smaller than what we saw, right? And we want to know, what is this value? Notice how similar this is to this graph up here that's on the table, right? And then it says, okay, those are the table entries. And so these here, these we're going to call the table entries. And then here it says the table entry for Z is the area under the standard normal curve to the left of Z, right? In case the graph wasn't enough, right? Just visually, in words, they say the same thing. Yeah. So what does that mean? It's the area under the curve, which is a probability, right? That's step number 1, recognizing that. So then from the table, the probability that Z is less than or equal to, the equal to is optional. Negative 3.36 is what? I like to take a straight edge because you can, fold your paper over or use some sort of guide. But here I can just highlight, so that's nice, right? Whole value, negative 3. First decimal is 3. Second decimal place is 6. So here at the intersection, it says that the area to the left of negative 3.36 is 0.0004. And very, very small. We would expect that. Why? We also said that in general, in life, anything that's more than 2 standard deviations away from the mean is going to be considered unusual. What's unusual? Well, the probability of seeing that is low, right? And so anything past a Z of negative 2 or positive 2 is typically considered unusual, right? Or at least worth exploring. So a Z of negative 3.36 is even more unusual, right? And so that's why this probability is so small, right? It's all review. Oh boy. Okay. Now, where were we? Oh, I guess I got a little overzealous cropping and deleting stuff. I deleted the blurb that we need to answer that question. Okay. Maybe I'll just do this. Copy. Call this the end of the review, picking up at the quality control example, which I'll bring in here. I'm surprised we're allowed to use Heinz. Maybe they spelled it wrong, but I don't think so. Usually it's something so close, but not really. At Heinz Ketchup Factory, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces. So that's probably what's posted on the label. Yeah. But we all understand that there's variability around that. We expect all the bottles to be around 36, right? So the normal distribution is centered around 36, but then we allow for some lighter bottles and some heavier bottles up to some maximum. Okay, and boy, that's not what I wanted to do. Okay, there. So now quality control goes in and they randomly select a bottle every 30 minutes. And if the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, it's considered to be, then it fails quality control, right? It's either too light, which you can't sell, or too heavy, which you don't want to sell. You can, but you don't want to, because then you're losing money, right? So there's this range where you're comfortable with putting out these bottles. And we answered this one. What percent of bottles have less than 35.8 ounces of ketchup? We went through and we translated the problem to a normal curve. And I said, okay, it's not going to make sense at all, probably in the beginning, right? When you read these problems and drawing out the curve, but eventually it will be helpful. So if you just stick with it, then you have a guide, okay? And so first thing I want to do is just draw out this normal distribution. Has a mean of 36, so I'll put 36 here, and a standard deviation of 0.11. Did we finish this one? Yes. Thank you. Then I can just grab it from here. Oops, that's not my crop tool. B. So then less than 35.8, just going to temporarily bring it in here. This area was 0.344, or sorry, 0.0. It's just going to go on a rant. Make sure you don't drop any zeros. What? Zeros don't do anything. Yeah. Sometimes. So this is from last day. So the probability of a bottle weighing less than 35.8 ounces is 0.0344. Okay. Why am I bringing that up? Well, for our next guest, what percent of bottles pass the quality control inspection? Okay. So now, usually what we do is we build on a previous part for these because they're quite long. Okay. So now, to pass quality control inspection, it looks something like this. 36 and sigma is still 0.11. Then 35.8 is the cutoff on the low end. And 36.2, which, as long as you're putting these values on the appropriate side of the mean, it doesn't really matter. You're just using them to visualize. And so usually I just give myself enough space to write whatever I need to write. And so 36.2, somewhere above the mean. even a little wonky, but it's just to visualize, right? And so now we want to know what % of bottles pass the quality control inspection. So as long as they're in this region, they pass. Right? Somewhere between here. There's some probability of passing, right? And so what do we want to do? And there's lots of ways that we can approach this. And like a lot of things, I encourage you to think about which way you get there naturally. And so just thinking about puzzle pieces, right? Knowing things like the total area under the curve is 1, right? That's a good one to have up our sleeves. Knowing that this area here is 0.0344. That's a good one to have up our sleeves, right? If we want the area in the middle, couldn't we take the same approach on this side and find this area, right? What's the probability of a ketchup bottle weighing more than 36.2? And then we have this area and this area. I can lob those off and I'm left with what I want. Right? What's another way that you could do it? You could, well, all the other ways are weird, but there's lots of ways that you can configure these areas, right?
Assume that both areas outside of our space are the same?
Yes, because of symmetry, right? But let's just confirm it. Once we get more comfortable, then you can say, well, I know that it's symmetric about the mean, right? But we're just starting, so we'll go through the steps still, but notice that I've gone down 0.2 and up 0.2, so feels symmetric about the mean, but you don't have to recognize that. You can just brute force it. Here we go. So find this area first. And like I said, there's lots of different ways that you can go about it. I'll add a page here. All right. I can draw out, might be helpful to remember that if you have some X, so some observation, and you want to end up at some probability, you have to use the Z as the gateway, right? Because you're using the Z table, so you need a Z, right? That'll kind of prompt you, but it's going to go like this. And then the Z is going to give you the probability. Okay. How are you going to get there? Maybe I'll bump this down a little bit. You're going to get there by Z equals X minus mu over sigma. How are you going to get from Z to the probability from the table? Right? So you need the Z to feed it into the table, and then the table gives you the probability, right? And surprise, surprise, later, we'll go the other way. I give you some probability. You have to use the table to convert it into a Z, so backtrack. Then use that Z to solve for X and get X, right? So we can work, I call that working backwards, because we always start here where we have an observation and we're working towards a probability, but we can just as easily go backwards. Okay? All right, so what do we need to do? I need to calculate Z equals X minus mu over sigma, which is on your formula sheet, right? And X is always the observation, right? The thing that I'm interested in the probability of. So in this case, 36.2. minus the mean, which is 36, divided by the standard deviation, which is 0.11. And okay, I already opened it. 36 divided by 0.11. I get, hey, that looks familiar. 1.81818, blah, blah, blah. What are you going to use as a prompt to remember how many decimal places you need? The table only has 2 decimal places, right? So you'll need to round properly to match the table, right? So there's no memorizing there, really. You get 1.82 since the table has 2 decimal places. Okay. So now I'm going to go to the table. I've got a positive value, which makes sense, right? Because we're above the mean. A negative Z means you're below the mean. Woo, where is it? Positive Z. So just make sure you're on the positive side. You'll know because all the probabilities are greater than 0.5, right? Because it's still giving you the area to the left, right? Software tables, it all just gives you the area to the left. So that's good to remember. 1.8. Start by highlighting that. And then I want 2.9656. Maybe I'll grab a copy of that. Mostly so I don't have to remember it. Now go to the table. So what phase are we in here? Right now, I gave it a Z. I used the table to find the probability. So then the probability that Z is less than or equal to 1.82 is 0.9656. Not exactly what we wanted, but it's okay. Now that I think about it, maybe we don't need to find this area first. Why? Nice. So, like I said, there's lots of ways. Some are more efficient than others, but they'll all work. So how about this? Or take this area. Right, gets really messy if I start to shade all the areas often. And so what I do is I take my line and I draw it up above so that I can kind of have some clarity here. But the table says that this area to the left of 36.2 is 0.9656. Recognizing that these are just puzzle pieces, I've got this big area here, right? And I want this area, so I can lob off the 0.0344 and be left with the area that I want, right? Or the probability that I'll write it. It's not something that I'm expecting quite yet. 35.8 is less than or equal to X. The observations are between 35.8 and 36.2 is 0.9656 minus 0.0344. 0.9312. This notation, this is optional notation for now. What could you say instead? In words, you could say the probability of passing the quality control inspection is 0.9656 minus 0.0344, right? 0.9312. Right? Whoo! What are some other ways that you could do it? Right? I started off and I said, well, we could find this area, right? Easier if you're using the symmetry, because then you know that this is the area, right? Because what is this area here? This is going to be, just give myself more room here, 1 minus 0.9656, which should be 0.0344, right? Also by symmetry. Let me just confirm though, so I didn't muck it up. Feels good. Okay. So then, also by symmetry. So recognizing that symmetry would have saved us a little bit of work, right? One more trip into the Z table, right? Doesn't hurt. But what could you have done? You could have said, well, the total area here is 1. I'm going to lob off 0.0344 on both sides, and then you would still be left with 0.9312. There are some other weird ways that you could do it, but let's not. All right. Okay. So now we have an answer. What we found was the probability of passing the inspection, but probabilities are the same as proportions, which are the same as the percentages, right? And so what percent of bottles pass the quality control inspection is going to be 93.12%. Right. Okay. Like I said, we can use the same method working backwards, right? And so let's just highlight the procedure again. We are given an X and we go and turn it into a Z by Z equals X minus mu over sigma. And then we use the table to turn it into some probability. Now, if I want to find a cutoff point, right, so an observation, then I want to find X, which means I have to start with a probability. And so now what we're doing is we're moving the other way. So we're given some probability. Oh, that's weird. Given some probability, and then I go into the table, I find the Z, right, backtrack, and then I use the formula kind of backwards, I guess, to find X. Yeah. So here we go. Body temperatures of healthy humans are distributed nearly normally with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. What is the cutoff for the lowest 3% of human body temperatures? Right. Might be good to know if you're, say, in the medical field. Oh, that's a very low temperature you got there, right? It's good to know what a low temperature is, right? And so let's see here. First thing you're going to do blindly just draw a normal distribution. As soon as you see something about nearly normally distributed, just draw a normal distribution. And even if you don't do anything else on that question on the test, I'll still give you half a mark. How about that? Hey, that's pretty good. You breathed on the page and you get half a mark. It's going to be worth like 7 marks though, so maybe let's do a little bit more. Okay. Let's see here. What's the next step? You're going to draw the mean. All right. The mean's always in the center, and you're going to draw it here, 98.2. You guys aren't in chemistry or anything. They always hate it when I say, oh, don't worry about the units. Forget about the units. Who cares? Emily, you can't say that. It's really important. Not for us. Standard deviation, I just kind of jot it down somewhere so that I have it close by. It doesn't connect to anything on the graph, but that's okay. It does, but it's too much work. So now we want to know what's the cutoff for the lowest 3% of human body temperatures. So now we're told that here, of course, this x-axis are body temperatures, right? So that's just a number line, okay? And so down here is where we find the lowest 3%. I'm going to force this area to be 3%. So now I'm going to force this to be 0.03. Right? And usually what I do is I like to draw a little X question mark there just to prompt myself that that's where I'm going. That's what I need to find, right? Okay. You could just scan the table blindly, I guess, until you find 0.03. But there is method to the madness on the table, right? It's going from negative 3.49 up to 0, and then you're on the positive page up to 3.49. And so if you think about how these probabilities would be increasing, right? The areas to the left are constantly increasing as you move across, right? Then you can find something close to 0.03 and then work backwards like that. So here we go. Is it going to be on the positive or the negative side of the table? That's a good place to start. Should be the negative. I never let you answer any of my rhetorical questions. Too much pressure. And nah. Okay. So here I am. Looks like gibberish. Whoa, trying to find 0.03, being super careful that you don't fall for a trap like this. It's a trap. 0.003. No. You want 0.03, which is somewhere closer to 0, right? And usually we don't get the exact value, but we get something like this. So it's somewhere between 0.0301 and 0.0294. Okay. And let's see if I can grab what I need here. Copy. Ooh, I've never done this before, but here's something wild and crazy. Copy, delete. Oh, let's see if that worked. Revolutionary. Aha. So I usually just write out, but this is just to talk you through it, right? And so using the Z table, we need to find the table entry closest to 0.03, right? That's rarely going to be available, right? Exactly, but we need to find the one that's closest. So we need to find the table entry closest to 0.03, right? And so somewhere in here, between 0.031 and 0.0294, I'm going to choose 0.031. Usually I have to use my calculator a little bit to see. There's usually one that's easy to figure out how far it is, and then when I subtract, it's hard. So, but this one is 1 away. That doesn't make sense, but it makes sense in my brain. This one's 6 away. It's not mathematically correct, but that's how my brain works. Aren't you a math teacher? I am. It's worked so far. But stats is my jam. Well, we can get away with this wishy-washy stuff. Right, you can use your calculator, see which one's the furthest away, right? As long as you pick the one that's closest, or honestly, if you just wrote down choosing between 0.0301 and 0.0294, if you weren't sure, I'm going to use 0.0294. Well, that's wrong, but as long as you followed through with that, you're okay, right? And so I won't be mad about that, right? As long as you tell me that I meant to choose the closest one, I knew to do that. Here's the one that I think is the closest. Well, it's not, but, and then you went with it. That's fine. That's okay. It's not life or death here. All right. So, yes. Where are we at in this little pendulum here? We've got a probability. We got it in the table. Now what's our next step is to backtrack to the Z that makes that happen, right? So now I'm going to use maybe a green here because and then I'll say the table entry closest to 0.03, and this is where if you got it wrong, as long as you tell me that, hey, this is the one that's the closest, 0.03 is 0.0301, right? In this case, it's correct. If you told me that it was 0.0294, well, that's all right. As long as it's kind of in the realm, right? And so, well, between the two options, right? I don't want to just have any value. Although I guess in theory, you could do pretty well on a test if you just memorized some standard answers. I'm like, well, I mean, the follow through is impeccable. Wrong initial values. Pick up on that though. So then I explain what I'm doing. I'm backtracking, so which corresponds to Z equal to negative 1.88, which corresponds to Z equal to negative 1.88. Add a page here. Nice. So now where are we at in our little pendulum? Now we're here. I've got a Z. So now the very last phase is to use the formula to find X. Okay. So Z is X minus mu over sigma. And I'm forcing Z to be negative 1.88 because that's what I want it to be, right? Trying to solve for X. The mean was 98.2. And the standard deviation was 0.73. Now it's a matter of multiplying the 0.73 over to the left and then adding 98.2 to both sides. So I get negative 1.88 times 0.73 puts me at negative 1.3724 is X minus 98.2. Ooh. You guys okay if I use my revolving door around the equal sign? It's a habit of mine. It's actually kind of a good habit. Usually you want to have what you're solving for on the left-hand side. So I just use my revolving door here and add 98.2 to get 96.8276. Right? You could answer the question now. What is the cutoff for the lowest 3% of human body temperatures? Right? The lowest 3% of body temperatures, human body temperatures. The lowest 3% of human body temperatures are less than 96.8276 degrees Fahrenheit. You don't want to do any rounding. You did all that work, right? And so why lose precision at the very end? We already lost it by only having 2 decimal places for Z, right? But that's just me belly aching. There. So now, if you took someone's temperature and you found that they had a 96 degrees Fahrenheit, 96 degrees Celsius, you're in trouble, but the other way, right? Right, so 96.8276. Anything below that is terribly low, right? The lowest 3% of body temperatures. So we can work in both directions. How about it didn't print properly. Same scenario, but what's the cutoff for the highest 10% of body temperatures? First thing you're going to do is draw your normal distribution. It's a good place to start. What would it look like? Well, normal, of course. Right. Look the same as the last one. Centered on 98.2 and the standard deviation is 0.73. And now we want to find the cutoff for the highest 10% of body temperatures, right? So now recognizing that here on this axis, you've got your body temperatures. And I want to find the value that forces this area to be 0.1. So give you a moment while I write out my blurb to find that area. What do you have to do here? There are 2 things that you could do, 2 obvious things that you could do. What's the first one? Well, how am I supposed to know? I have them internally. What's the first one? You could say, well, the table only gives me the area to the left. So what's the area to the left if the area to the right is 0.1? Well, it has to be 0.9. So you could do that, right? You might do that. Try to do it like this. And then you would find the table entry closest to 0.9. That's fair. What else could you do? You could rely on the symmetry, right? And so by symmetry, you could say that negative z closest to 0.1. So what would you have to do? Closest to 0.1. But then you'd have to drop the negative because you want to be on the other side, right? But you're relying on that symmetry. So whichever way you do it, you're going to find the same z. So let's see here. 0.1. Which one should I do? Usually I do this one because it's kind of more straightforward. So I'm going to find the table entry closest to 0.9. So now using the table, using the z table, this is how I would formulate my answer in my work. I just explain what I'm doing, and that's always a good thing to do, especially if you're a student. Using the z table, we find the table entry closest that doesn't look like closest to 0.90 is, and now I actually have to go find it way up here. It's gonna have to be on the positive side, right? Because it's greater than 0.5, so I know that. And 0.9, looking good. Okay. Looks like I'm choosing between these two values here. Uh-oh. This one's 3 away and this one's 15 away. Math, right? Let's see here. Do my same cheater style. Bring it down. Whoa. Am I right in doing this one? 0.8997? Or is it the other one? I think so. I'm going to do 0.9 minus 0.8997. 0.0003. Okay, so 3 away. And then 0.9015. Yeah, I'm feeling good. -3. Yeah. Even if it's not right. If I say it is and I follow through, still kind of right. Which corresponds to shrink it down a little bit to z equal to 1.28. Gonna try to keep it on just the one page here. So now I have the z. Now I need to find my x, and on the formula sheet, there's usually a worked out formula for x if you don't like doing the math every time, but you're gonna have to do it like once on the test. So I like to have fewer formulas personally, but z equals x minus mu over sigma. Z is 1.28. X minus mu was 98.2 divided by 0.73. Times 0.73 plus 98.2, just going straight for the jugular here, 100.21 degrees Fahrenheit. So any temperature over 100.21 degrees Fahrenheit is in the top 10%, right? Or the 90th percentile, if you want to go back to percentiles, right? Okay. Oh, I'm sloppy. Okay. Did I get the 1.28? How far back do I have to go? Times 0.73 plus 98.2. Boy, well, I didn't like that. Let's see here. Yeah, thanks. Just sloppy. That? Oh, yeah. Close enough. Yeah, they'll all be very similar. As long as you show me that you understand the method, we would use software to do these calculations anyways, and it's rarely wrong. And so this is quite imprecise, but it's the best we've got. So for in-person testing, on paper testing, I should say. Okay. There was one term, I'm constantly changing how I teach this stuff. And there was one term I was so mad about using all these paper tables and they're so archaic and whatever, that I said, you know what? We don't need the tables. We can just use the 68, 95, 99.7 rule to get approximations. Crazy, right? Well, let me tell you what it is first. This is also called the empirical rule. But usually we just call it the 68, 95, 99.7 rule. Now, it's a rule which says that as long as your data are nearly normally distributed, then about 68% will fall within one standard deviation of the mean. Yeah. About 95% will fall within 2 standard deviations of the mean. And then if you move out 3 standard deviations, you've covered the central 99.7% of the curve or the probabilities, right? Which is where that 6 sigma came from, right? 1 standard deviation, 2 standard deviations, 3 standard deviations, a total of 6 far away. Just remember that it's possible for observations to fall 4, 5, or even more standard deviations away from the mean, right? But they're very rare, right? So the probabilities are very, very small. As an example, what's the probability of something more than 3 standard deviations above the mean? Using the 68, 95, 99.7 rule, we can figure that out, right? The total area under the curve is still 1. I've got the middle 99.7% or 0.997, which means I have 0.3%, so 0.003 split in half because of symmetry. Oh boy. The probability of an observation more than 3 standard deviations above the mean is going to be, how would we find it? Just using these values, right? Not the table, although you could if you wanted to. You can confirm it with the table. Right? The table is more precise, but not as precise as software. We've got this range of precision. I would take 1 minus 0.997 to find the area in the tails, right? Which is, let me just confirm. I don't want to muck it up again. Of course, my calculator just gives me scientific notation. Or a fraction. None of those are helpful to me. Now I have to move the decimal. 1, 2, 3. Yeah. Okay. But this is split evenly among the tails. Amongst the tails, maybe. I don't know. So then 0.003 divided by 2. Oops. Same thing, 0.0015. 1, 2, 3, yeah. So you can use these approximations to say, okay, if you have something that's 3.5 standard deviations above the mean, you could just say, well, that probability is less than 0.0015. Right? And then use software for more precise probabilities, right? So knowing these and remembering that this is for the central 68%, 95%, 99.7%, right? And then remembering that the remainder is split evenly amongst the tails, right? Then you can get some pretty reasonable approximations for the probabilities. In the lab, you'll confirm this, right? So I give you a data set and surprise, surprise, it's normally distributed. You have to check that. Then what do I get you to do? I get you to find what proportion, percentage, probability, right? What proportion of the data is within 1 standard deviation. Should be close to 68%. But not necessarily exactly 68%, but it should be hovering around there. 2 standard deviations should be roughly 95%, right? 3 standard deviations should be roughly 99.7% if we had an infinite sample, which is hard to wrap your head around. Okay. So if we have a distribution like this, SAT scores, for example, they're normally distributed. That's where we started with the normal distribution, right? And so what could we do? If I know the mean and the standard deviation, then I could say that roughly 68% of students score between 1200 and 1800 on the SAT, right? Moving out 1 standard deviation from the mean on either side, right? If I go at 2 standard deviations, so 2 times 300, 600 on either side, then I'm between 900 and 2100. And then finally, 99.7% of students score between 600 and 2400. I don't know what the SAT is out of. That'd be helpful. Let's say it's 2500. I don't know. Maybe it's 2400. Often there's a cap, but theoretically it keeps going to infinity still. Okay. I hate all these. Which one of these is false? Those are harder for some reason, right? You can pick out a true thing, but can you pick out 3 true things, which is the same as picking out 1 false one? Huh? How about that? Okay, which of the following is false? The majority of z-scores in a right-skewed distribution are negative. Uh-oh. Time to wake up. And so pleasant, too. This is going back to how do skewed distributions behave, right? So if I have a skewed distribution, has to be a right skew, looks like this, right? What happens to the mean in a skewed distribution? The mean is pulled in the direction of the tail. Which means that the z-scores are still going to be negative if they're below the mean, right? But now, because I've pulled the mean out towards the tail, that's just the behavior of these distributions, then the lump of this data, right, those are all going to be negative z's. So here I get negative z's, and here I get maybe positive z's, right? So the majority of z-scores in a right skewed distribution are negative. That's true. Took a lot of work to get there, right? To think about it. All right. So that's not it. Surprise, surprise, it's not the first one. Whenever there's a pick the false one, it's rarely the first option. In skewed distributions, the z-score of the mean might be different than 0. Z-scores. Let's see here. Z, regardless of the distribution, you can always calculate a Z, even if it's not for a normal distribution. But if X is the mean, how far is the mean from the mean, regardless of the shape, right? How far is this mean from the mean? 0, right? And so that's not true. But let's confirm that the other 2 are true, just for fun. For a normal distribution, the interquartile range is less than 2 standard deviations. Okay, that's relying on quite a bit from before. Let's remember that the interquartile range is the distance between Q3 and Q1, but the distance between the third quartile and the first quartile is always going to be the central 50%, right? And so here, this is the central 50%. Whereas from the 68, 95, 99.7 rule, 2 standard deviations is the central 95%. 2 standard deviations is the central 95%, which means that the distance between those has to be larger than the interquartile range, right? And so that's why this is true. Last one, z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution. Well, that's why we use them. So that's true, right? Using 2 plus minus 2 as a cutoff, right? Any z that's more than that in either direction is going to be considered unusual. So we were right to pick B as the false one. Had to do the work. Oh. Can I introduce this experiment and then we'll use it on Wednesday? How about that? This is 4.2, which is not the only reason I kept it. Usually I kind of shove it to later, but they introduced this experiment that we're going to rely on in the binomial distribution. So here we go. It's called the Milgram experiment. And there's been tons of experiments similar to this. But Stanley Milgram, a Yale University psychologist, conducted a series of experiments on obedience to authority starting in 1963. So there's an experimenter, there's a teacher, me, and the subject, you, but they're actors actually. And the subject, so the experimenter orders the teacher, the subject of the experiment, to give severe electric shocks to a learner each time the learner answers a question incorrectly. The learner's an actor, so they're not actually being shocked, but the teacher doesn't know that, right? And so then we get a good gauge of kind of how willing to be obedient we are. So these experiments measured the willingness of study participants to obey an authority figure who instructed them to perform acts that conflicted with their personal conscience. Okay. Milgram found that about 65% of people would obey authority and give such shocks. I like to think I'm better than that, but what they've found through a series of studies is that over the years, additional research suggests that this number is approximately consistent across communities, time, doesn't matter who you are. Roughly 65% of us would just do as they're told, which, yeah, it's fair. But even if it goes against your own kind of beliefs. Okay. So when we're doing this, each person is going to be a trial, right? So each teacher that they're testing on or kind of observing is considered a trial. And what we need to do is we need to identify a success and a failure, because that's what we're trying to model, okay? And usually the success is something morbid because it's the success that we're interested in, okay? In this case, they took the lighter route and said a person is labeled a success if she refuses to administer a severe shock, and a failure if she administers the shock. So if 65% are giving the shock, then 35% are not, right? Just in general. So the probability of success is 0.35. Yeah? So when each trial only has two possible outcomes, then it's called a Bernoulli random variable. Yeah? And so only two possible outcomes, then we call it a Bernoulli trial or a Bernoulli random variable. So if we wanted to repeat this experiment, right, we could use these probabilities to find other probabilities using the probability section that we've already covered, right? Back to that, I know. So what's the race against time here? But she only wants to sample people until she finds someone who will not inflict a severe shock. What's the probability that she stops after the first person? Well, 0.35, right? 0.65 do, 0.35 don't. The third person, person one, person two, they don't. Or they do, and then the third one refuses, right? The 10th person, you can do the same thing. No, 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 yes, or success. So the geometric distribution describes the waiting time until a success for these independent, identically distributed Bernoulli random variables. Now, the only thing I needed to take away from this is the independence. So the outcomes of the trials don't affect each other, right? Each teachers individual or independent of the next. And identical, meaning the probability of success is the same for each trial, which is what we're assuming. In general, if P represents the probability of success, then 1 minus P represents the probability of failure, sold. And N represents the number of independent trials. Then if I want to find the probability of success on the nth trial, then I need to have N minus 1 failures followed by 1 success, right? In general. What if we have something that's not obviously a Bernoulli trial right away? What if we have something like calculate the probability of rolling a 6 on the first try on the 6th roll of a die, or for the first time on the 6th roll of a die using the geometric distribution? You can, even though there are 6 possible outcomes, you could boil it down to a 6 or not a 6, right? And then all of a sudden you have a success failure situation. And we're going to use that a lot, where we just boil it down to a success failure. And so here, you're going to say, yes, why not? And I'm out of time, so we'll pick up there on Wednesday. Just motor through that geometric. I think there's no. All right. If you have any questions, let me know. Otherwise, see you on Wednesday.